Okay, we're going to start unit section 2, which is differentiability, and basically it's just going through when does it have a derivative, when does it have a slope. Um, so that's the main thrust here. Differentiable by definition is a derivative exists for all values on its domain, meaning all values of x. A couple of the ways to view it graphically, you're saying it's smooth on all points of the curve. It has a slope everywhere, um, but to prove it, to justify for all values of x, the limit as x approaches a on the negative side of the slope must equal the limit as x approaches a on the positive side of the slope. Does not also require it to actually be at the point. So just these two parts. So in other words, the limit has to exist. This is no different than continuity. It is continuity of the derivative. So the only significant difference is we don't actually have to have a point there. So this is kind of the proof that in fact you have it as long as it's for all values of a on the domain. The catch-all is it's usually differentiable everywhere. So what we do is we focus on where it's not differentiable. There are four key element places that we would find things that are not differentiable. One is at corners. Any corner is not differentiable. What kind of functions create corners? A key one is the absolute value. Any absolute value creates a corner, and piecewise functions. Piecewise fun. Those guys are always fun. Now, piecewise doesn't necessarily imply it's going to have a corner. It just implies it could. Absolute values always have corners. So let's take a peek at the absolute value curve. It looks like this. If you look right here, it has a corner. So I would say it's not differentiable at x equals 2. Why? Because the limit as x approaches 0 on the negative side of the slope does not equal the limit as x approaches 0 on the positive side of the slope. In other words, the slope on this side is -1. The slope on this side is +1. Therefore, the slope here is not the same on either side. Second place where you'd find not differentiable would be at what's called a cusp. And a cusp occurs in functions like this: x to the 2/3, x to the 4/7, x to the 6/11. Key elements that indicate to me it's going to have a cusp is the fact that it has an even power with an odd root. Even power, odd root. And the fractional power should not be top heavy. In other words, it has to be a fraction in between 0 and 1. These fractions here are all fractions between 0 and 1. So what do those look like? If I was to graph y equals x to the 2/3, it would look like this. It would look like a birdie. Okay, it's not called a birdie. Please don't go to college saying I see a birdie. Okay, this guy is not differentiable here. Again, notice I can apply this limit deal where the slope of this side is clearly not the same as slope on this side. So at that point 0, it's not differentiable. So not diff at x equals 0. Now the birdie, or the cusp, can be moved to other locations. All I have to do is do a translation. So something like x minus 2 to the 6/11. That curve looks exactly the same, only it's been translated over to x equals 2. So here, this one is not diff at x equals, 2. Okay, so there's 2. So I'm going to go ahead and skip part. I'll go down here and we'll look at those pictures here in a second. We're going to do the 2 more. There's 2 more types. The next type is a vertical tangent. These are the most commonly this is the most commonly misunderstood ones. They forget these all the time. They're hard to see too. So very similar to the cusp, a vertical tangent or vertical tan has a function that has a fractional power between 1 or 0 and 1. So something like this. Sorry. Okay. So all these are examples of functions that have a vertical tangent. You're welcome to put those in your TID3s to observe those. Again, notice the fraction is odd over odd, where cusp was even over odd, and they're not top heavy, so they're between 0 and 1. Okay, what does a vertical tangent look like? If I graphed this function, x to the 1/3 power, what happens is it's a cubic function. As you go along, right here at 0, the slope gets really, really large. Observe how the slopes are small, small, bigger, 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 till it gets to right here. Well, you can't say the slope is infinity. That doesn't make sense. It just doesn't. So right at that point, at this very moment, at 0, it has a slope that's infinitely large. It's a vertical tangent. And at that point, it's considered not differentiable because it's not a number that exists. But all these other points on the curve do have it. So what you'll see again is you'll see the slopes getting bigger, bigger, bigger to right here. They get to an infinity. That's not a value. So therefore it's not differentiable there. And then it goes all the way through, and all those values of these slopes all exist. Just like all these existed. Okay, so I would say not differentiable at x equals 0. Again, a simple translation, say x plus 5. All that does is move the vertical tangent at -5. See, right there. So right here at -5, what happened was the curve all of a sudden had a vertical tangent of infinity, which is not non-existable. So I would say there it's not differentiable at -5. The last one, if it's not continuous, it's not differentiable. So the fourth type is where it's not continuous. Or, big boy words, it's a point, you see a point of discontinuity. And a review of those. What are some points of discontinuity? Well, let's see. We had removable, or a hole. We have infinite. In other words, it has a vertical asymptote. And the last one is jump, usually created by a piecewise function. So we've already discussed points of discontinuity and removable. So removable would look like this, and the equation would be something where you can cancel. So if I had something like this, that function right there is x minus 1 over x plus 1, x minus 1. Which implies at 1, you don't have a vertical asymptote. What you have is a removable. If it's not continuous, it's not differentiable. This other one here, it is in the denominator. That's going to imply an infinite point of discontinuity because it's a vertical asymptote. X cannot equal -1. Therefore, it's a vertical asymptote. If it has a vertical asymptote, it's not continuous, which implies it cannot be differentiable. One thing you can't say, and I'm going to highlight this, is you cannot say because it's continuous, it's differentiable. Okay? Just because something's continuous does not mean it's differentiable. Now, the other way around does work. If I say something's differentiable, then it has to be continuous. Because one of the reasons it's not differentiable is continuity. So continuous does not imply differentiability, but differentially does apply continuity. Okay, the last one is jump, and we'll see illustrations in the example 2, 4, and 8, especially 8. So I'm going to sketch these real quick from the book. If you look at example 2 in the book, that's on page 114. It appears like this. Right there is 2. See, this function here is differentiable everywhere, but not at 2. Why? Well, because at 2, there's a corner. Therefore, the limit as x approaches 2 on the negative side of the slope does not equal the limit as x approaches 2 on the positive side of the slope. Therefore, not diff or differentiable at x equals 2. Your next example is number 4 in the book. This one can be qualified as a corner because the one side is a line, and then you have what looks like a part of a parabola or something there. Again, this one, I'm sorry, this is at 1. There's 1. So this one is not differentiable. And if you're going to justify it, this is always the means. The words don't necessarily mean much, but I would say instead of 2, I would say at 1, not differentiable. Why? Because the slope on each side is different. Hence, you would say not differentiable at x equals 1. The last one's a little bit more complicated, so I'm going to sketch that one. Give me a second here. I just feel so excited that I get to sketch this graph. 8. Okay, so 8 looks like this. It's got a looks like a absolute value function, open there, closed here, and you got a -1 here, and then it looks like, I don't know, some random old thing like this. And the function begins at -2 and ends at 3. And I think I'm missing something. Oops, I totally messed that up. I apologize. Wrong curve. Let's get rid of this. It's closed at 0, loops up and comes around to 3, but at 2, you have a hole or a removable point of discontinuity. And there is a point down here, and that occurs at 2. Okay, so this guy, where is it differentiable? Well, it's differentiable from the interval from -2 to -1. I don't have brackets because I can't include the -2. I can't say over here at this particular point that on this side the slope's the same. I don't know anything about it. So I know it's differential from here to here. It's not differentiable at -1, corner. So union, notice how I don't have a bracket, I have a parenthesis. That means it doesn't get included. From -1 to 0. Well, at 0, you have a jump point to discontinuity. If it's not continuous, it can't be differentiable. So that one can be included. But then you go from 0 to 2. That is a continuous, no corners, no nothings. So it's continuous or differentiable from union from 0 to 2. And then again, a removable point of discontinuity implies it can't be differentiable. So I can't include the 2. Union, and let's finish this one off, 2 to 3. 3 is at the end. Again, it's closed here, which implies I can't tell you what's going on this side with the slope. I don't know if it's a corner, I don't know what's going on. So therefore, I don't include it. So that concludes this section of Unit 3A.